This is AP Calculus 3-4. We're going to find the derivatives of inverse trig functions. Now, just a little bit of review. If you have the inverse sine function, that's understood to be sine -1x or arcsin x. They mean the same thing. So any of the inverse trig functions can be interchangeable. You can use sine and the little -1 symbol for the inverse function, or you can use the arc sine, arc cosine, arc tangent, and so on. So I'm going to be interchanging those within my problems just to get you used to them being the same thing. They mean exactly the same thing. We will memorize these for the AP Calculus test. I usually allow my students to use these in their notes at first until they get comfortable, and then the closer we get to the test, the more they need to really have them memorized. So to start this out, I'm going to derive the arc sine formula for you so that you can see where it comes from, and then after that we will just use these forms to find the derivative of inverse trig functions. I want you to pause the video, get these things down, the ones that you have to have memorized, just have them available so that when we get into doing some examples, you have these readily available to look at and compare so that you know where the answers are going to be coming from. So now that you have these available, we're going to derive the arc sine derivative. I'm going to do that first, show you where it comes from, and then from there on out we'll use the rules that you have here. So this just tells me to find dy over dx, find the derivative, if y equals arc sine x. So we know from inverse functions and our work with inverse functions from Algebra 2 and Pre-Calculus that if we have an inverse function, the inverse of arc sine is sine. So in order to get the inverse in terms of sine, all we have to do is switch our x and our y and change it from arc sine to sine. So what that means is if y equals arc sine x, then sine of y equals x. And if we're trying to derive the derivative, we're just going to find the derivative of each side. So I'm going to take the derivative of the left-hand side and the derivative of the right-hand side, and I'm going to use implicit differentiation. So to do that, the derivative of sine is cosine. We have the y, but when we take the derivative of cosine, we also need to find y prime, or dy over dx. That's what we're trying to find, is dy over dx. And then if we take the derivative of the right-hand side, that's just 1. And then to get the dy over dx by itself, dy over dx is equal to 1 over cosine of y. And then we need to think about cosine of y. We can replace that using the trig Pythagorean identities for our trig functions. We know that sine squared x plus cosine squared x equals 1. So if this is 1 over cosine y, then that's the same thing as saying sine squared y plus cosine squared y equals 1. It doesn't matter what we use for that angle part. If we want to get cosine of this by itself, cosine squared y equals 1 minus sine squared y, and then the square root of both sides, cosine of y, would be equal to the square root of 1 minus sine squared y. So I can replace cosine with what it equals. So dy over dx equals 1 over the square root of 1 minus sine squared y. And then from what we had right here, remember we had sine y equals x. So since x equals sine y, here we have sine squared of y. So dy over dx is 1 over the square root of 1 minus x squared there. So we have derived the derivative of arc sine just using some review information here and doing some substitutions. So this is good when your arc sine when you have the what I call the angle part of x, then the derivative of x is just 1, and we've got the x squared here. What's going to sometimes happen is we're not just going to have an x here, we're going to have some function of x, like 2x squared or 3x to the fourth. And what you need to understand when you're dealing with these formulas is, once you figure out what the u part is, that derivative of that u part is going to be on the top of your functions. And we have that here. The derivative of x is 1. So this is your u prime over 1 minus u squared when you're comparing that to this. But that's just the simple basic sine or arc sine of x derivative. So these are the ones, or these are the formulas that we're going to use to do the more complicated functions. You just have to understand that you have to identify what that u value is, and then you're going to find your u and your du. Your du or your u prime always goes up on the top of your inverse trig derivatives. So here I have a couple different examples. In this one, your directions will be to find g prime of x, or find the derivative of g of x. And then in this one, they want you to just take the derivative of arc sine the square root of x. So to do this, first we have to identify what our u is. In this one, our u is 5x, so our u prime is going to be 5. So if we use the formula, this is an arc cosine, so g prime of x is going to be equal to, all right, arc cosine of u is u prime, or negative u prime. So negative u prime is 5, that goes on top, over the square root of 1 minus u squared. U was 5x, so u squared will be 25x squared. And that is our derivative of that inverse trig function. For this one, our u is the square root of x. Our u prime is 1/2 times x to the negative 1/2, or 1 over 2 square root of x. And then if we use the arc sine formula, u prime would be on top, so u prime would be 1 over 2 square root of x, all over the square root of 1 minus u squared, which is x. And then understanding that that is on the denominator, we can invert and multiply that. So that's understood to be over 1. So if we invert and multiply, we have 1 over 2 square root of x times the square root of 1 minus x. And since we have two things on the denominator underneath the square root, we are allowed to multiply those square roots together. So that would give me 1 over 2 times the square root of x minus x squared for my final answer. So sometimes you might have a problem like this. Y equals arc sine x plus x times the square root of 1 minus x squared. And the directions are to find the derivative, or find y prime. This could be set equal to f of x, and they could ask you to find f prime of x. But basically, they want you to find the derivative. So for this, this is no different than our polynomial functions. We will take the derivative of each term separately. So for this term, we're going to use the formulas over here. For this term, look at that, we've got the product rule. So you're going to use the product rule for that. So for the first term, arc sine, your u is x, so your du will be 1. So y prime is equal to u prime is 1 over the square root of 1 minus x squared, because u is your x squared. Here we have to use the product rule. So we're going to have plus the derivative of x is 1 times the original second part plus the original x times the derivative of the second part. Now for that, we're using the chain rule. Remember, that is 1 minus x squared to the 1/2. So we will have 1/2 times 1 minus x squared to the negative 1/2 times the derivative of the inside part, negative 2x. And then we're going to simplify that as much as we can. So we've got y prime equals 1 over the square root of 1 minus x squared plus that square root of 1 minus x squared that's understood to be over 1. We're going to get a common denominator to simplify this a little bit. So I need to understand that that's over 1. I won't leave it there. I'll put the common denominator in. And then over here, we've got a negative 2x times x, and then 1/2 times the negative 2. The 2 and the 1/2 cancel. But on top, we've got a minus x squared, and on the bottom, we have the square root of 1 minus x squared for that 1 minus x squared to the negative 1/2. So if you notice here, these both have a common denominator. In order to add them together, this one needs the common denominator as well. So I'm going to multiply the bottom by the square root of 1 minus x squared. If I do that on the bottom, I also have to do that on the top. Now, notice what happens when you do that on the top. Doesn't the square root just cancel out? So what we have is y prime equals 1 over the square root of 1 minus x squared plus 1 minus x squared over the square root of 1 minus x squared minus x squared over 1 minus the square root of 1 minus x squared. Then if I combine my like terms on the numerator, the denominator is just going to be the square root of 1 minus x squared. On top, I have 1 plus 1, which is 2, minus x squared minus x squared. So that's minus 2x squared. So here, if I take out a 2, I have 1 minus x squared. And if you look at what you've got there, this is 1 minus x squared to the 1/2. This is 1 minus x squared to the 1. So 1 minus 1/2 is a 1/2. So y prime, for simplest form, is 2 times the square root of 1 minus x squared. That is the simplest form that we can get that into. In this problem, they might just ask you to simplify or solve it. You need to recognize what you've got here. Notice this is the alternate form of the derivative. So our first task here is to identify what our f of x function is. And if you look at this, knowing the limit definition for a derivative, hopefully you see that the f of x function is tangent negative 1 of x. So our f of x function is tangent negative 1x. So if they're asking us to find the limit as x approaches 1/3, aren't they really asking us to find f prime of 1/3 for that function? Okay, so they're asking us to find f prime of 1/3. Well, we know that f of x is tangent negative 1 of x, or arctangent of x. So f prime of x, we're going to follow the formula. Here's arctangent. Our u in this case is x, so x prime would be 1 over 1 plus u was x, so u squared is x squared. And then we have to plug in 1/3. So we've got f prime of 1/3 is equal to 1 over 1 plus 1/3 squared. 1/3 squared is 1/9. 1 plus 1/9 would be 10/9. So we've got 10 over 9. And then to invert and multiply that, our f prime would be, or f prime of 1/3 would be 9/10. So they gave you that problem. They kind of disguised what they were asking you for. You just have to remember how to recognize that alternate form of the derivative.